Namaskar, good morning, Salaam Alaikum, Sarvudda Bakar, Sat Sri Akal, Bismillah Rahman Rahim. Good day, good start. This is Engineer Suraj Singh speaking from Bharat, India, addressing all my friends throughout the globe. And July 23, 2020, another day of life with this year and profession. Important is how to use profession, how to use time. It's more important how to participate in the world, how to manage through people, how to manage through systems, institutions, and society. Life never remains constant. It goes and moving and moving and moving. No one can guarantee for future, but present can be utilized. That is very significant importance, and we should understand facts of life. Life keeps on moving, that's good, that's fine, and we do have a duty to understand what we are talking of. Important is we should be busy, we should be doing something in no relation to money earning, but to dispose our service to whole world, and particularly when you belong to engineering, you have a lot of responsibility in addition to normal responsibilities that we have in this world. Engineering, management, and specific life that we say. Engineering is very different profession, as you say every time. This profession is original. I believe that this profession is not relative. It's original. That sense we should have, and that's what I usually think about that. So this is engineering. I have to move forward little because management, system and changes and organization and challenges, human thinking, last resort. Only resort you can say, general specifications, total systems, quality, structured quality, I can say soil engineering, most important item for whole world. Report, FIDIC, if time permits. My intention is little concentration on soil engineering in addition to management, because soil is everything. If you place little mind, and it can make you, it can break you. It can make our life, it can break our life. That's very important point that we should understand. Soil unfortunately has been understood in different manner rather than its true value not given to this. Means soil has been taken as if it's something dirty, which is not correct. Soil is very important part of everybody's life. And without soil, I am not there, you are not there, in fact is that. Without soil, we cannot even sleep, because soil supports everything. This point we have failed to understand in our real lives. Just because I am beginning, I am speaking a little slow, and today I can say I'm getting little more confidence because of a little better weather. I don't know what happens after some time. It seems to be a little better than yesterday, and also better. Yesterday was worst, and the day before yesterday was not good. I'm interested to talk about engineering management and management of engineering, both. When we say engineering management, it's not exclusively related to engineering only, because engineering is general word. Now I'm talking of engineering, you can say, is a word like because this word has been used, is being used to indicate profession of engineering, profession of various branches of engineering. There are various branches of engineering, not one actually. Civil, electrical, mechanical are basics, we know that, but there are many more branches. Electronics, IT, you can say, agriculture, aerospace, automobile, and aeronautical engineering, and mining, or you can say agriculture engineering. So many, means more than 15 branches of engineering, and it can be more in future, nobody knows. But it's not question of branch, it's question of development of human lives, development of world, and say. Management doesn't mean just to do something in a defined way for best profit. No, that's not management. Management is something, we should say, it's obsolete term, I can say, obsolete term. Rather than management, we should say engineering something, because everyone does something that's useful for society, economies and world. If it's not useful, we won't do it. That's also a fact of life. When I say fact of life, means something that works for everybody. Fact of life means you have to stay somewhere in this world. You have to stay on surface of earth, and you must have small room to sleep. Otherwise, you have to sleep in open to sky, and whole world is your room, which is an imagination only, because you won't be allowed to even sleep like homeless person. Police will come and kick you out from that place, and there is two possibility. Thinking that you are a criminal, rather than you are a criminal, you are a hapless person, there is no place. That point has been missed by world society. Well, when we are talking of engineering here, and particularly soil engineering, I should relate soil engineering to engineering management, because word soil, we say there's some phrase in our country, they say he's so lucky person, he's so fortunate person that he takes out soil and converts to gold. Do you understand? Means he is so fortunate by blessings of Almighty that if he puts his hands into soil, he takes out gold. Well, phrase is very good in a sense to explain to others that soil is zero and gold is everything. This means is that when soil has no value, if he puts in hand in soil, he converts it to gold. That's a proverb. But in fact, this proverb is real to my analytical mind. It says this is real. This means you extract gold from soil. It's not. You imagine that this is an activity. You extract gold from soil. This means soil is richer than gold. Take its valuation that way. If you are extracting golden value or gold's equivalent value from soil use, this means soil must be having more value than gold. And that is what I want to say. Soil is gold, soil is diamond, soil is platinum, soil is everything in our life. But we do not consider it in its value. We consider it as it is nothing. It's soil. It's a soil person. Mitti ka Madhav. Yes, that's right. A statue of soil. Is a statue has no mind, is only soil or rock. We generally say that in joking language. Well, no problem at all. No problem. We call a subject that's known as foundation engineering for purpose of construction. When we talk of construction, we talk of when you say I'm going to construct something, that construction is not site construction actually. That is not site execution. That construction doesn't indicate that. Though it's construction, but that indicates some project. The construct is. It's general what construct means. If you say in its summarization or analytical, construct, C-O-N, con, and S-T-R-U-C-T, construct. There are two terms in this, con and concentration on structure, you may say, or you may say, concrete structure. You may say anything. We use construction for some, but we have to construct it. This means we have to structure it. It's not field construction. Just understand. Article meaning of this, article analysis meaning of this, article analytical meaning of this is construct. You are relating to structure. It doesn't mean it is concrete structure, whatever structure it could be. So construction is concentration, or concrete, or you can say whatever concrete result. Concrete doesn't mean material of concrete I'm talking certainty of result. That is construction. So I am giving you different concentration here, means structure. Formation is construction. And what is backing there is, backing is philosophical design, backing is philosophical consideration of design, and real design, and delivery of this design to some person, so that person goes to some field, some plot, and works there and produces that design into physical entity, which is called structure. But this is related to foundation engineering. And foundation literally meaning is, foundation means something we have to build on which something else rests. Generally in our engineering we call foundation as substructure, and above structure, above ground, that we call superstructure. This means superstructure rests on, we are saying rests or connected to foundation or substructure. Here we are saying substructure and superstructure. This means substructure plus superstructure equal to working structure. Substructure, though we are naming substructure, but actually it is superstructure, and that one should be structure. Because functionally we call superstructure, it is not super, its purpose is not super, it is useful identity, useful item, useful product, while foundation is actually supreme structure for this. Or you can say supporting a structure for that structure. So we have to think this way. Don't go to real meaning, go to this way. The foundation is having more significance than real structure or superstructure. But foundation engineering is very difficult to understand, because it's not foundation alone or foundation structure. We can say the structure of foundation. The structure of foundation is not alone, is not in isolation. That is main point. Because foundation structure is connected to connected to another material which we call soil. Somebody may ask, how does it mean that, how does it, how do you answer that it is material? Question is right. How it is material? Can you define it? Frankly speaking, an only material that is more important and most important and additionally important than foundation is soil strata, soil body, soil mass, which receives stresses from foundation and transmits those successfully to this body of soil. And then this disappears somewhere. We do not know where it is gone physically, because that forces on foundation are taken by, are absorbed by soil body. That soil body is not small piece. That soil body is very big structure created by nature or created by some other agencies like wind, like you can say depositions, sedimentations, like by volcanoes or whatever actions of these natural agencies do this. We have to analyze and understand what actually we know about this. Okay, books speak something, but books are books, professors are professors, and students are students. Problem remains that many properties of this soil material were not researched by engineers or scientists. These were researched by some agriculturists or some other people who never ever had any educational background of engineering or basic sciences. This is great achievement by those people in those times when they did it, that despite having no formal education, they delivered to world something which still we use today. We rely upon that information, and as we are understanding classification of soil, what is this and what is that, what is this limit and what is that limit, still we are dependent on those people's theories we got from them through books or otherwise. This means it's not alone books that helps you. Books are written by people who have done something, and you can be one of them, I can be one of them, everybody can be one of them. But we have stopped thinking. As much as we are qualified, we are educated formally and have experience in addition to that, we have started reducing thinking power. We have debating power of what literature is available, why it is available, what's the reason behind that. We are short in our caliber to add to our research activities. Rarely research goes on in our field, in our engineering, civil engineering. Research is not on high profile. It's done by those who are university professors, not real engineers. And engineers very rarely conduct researches, and that's why formula which was available 100 years before is still applicable successfully, because no research is done. It's engineering, you may say now, practical engineering, to be very frank. Its basic vista of expansion of thinking based on thinking does not exist. application of whatever we have, we beat about that all the time. While engineering is a freedom principle, it's a freedom profession. It's a field that is free to think. But no, it's not free to think. It's bound by people's defined knowledge and not to expand that knowledge, unfortunately. Because I am talking of something you do not accept, I know, do not accept, but you cannot reject that soil is a material. And I have not seen this material, I have not seen in engineering books of material sciences that soil has been given that degree of domination it should have. Domination is there of aggregate, concrete, this material, that material, cement, aluminum, brick, block, all that, timber, and this. You will find every material there, but father of this material, that's called soil, because all these materials which are given in box do come from soil only. Soil which is naturally born minerals, particles. Soil is very unpredictable material. We cannot predict, its conduct in future, how it shall. Because soil never stays permanently at one level. It moves on, and we know that soil can't be changed, and we can't understand with guarantee what we say today. It will be same after 20 years, 30 years, 40 years. That is natural conduct of soil. We may site a building, say 5 meter below, 4 meter below, 3 meter below today. It doesn't mean that is final forever. That data may be reliable today. It may be in better form after 10 years, or it may be in worse form after that time. Both possibilities do exist. This point we cannot say, we have no right to reject this point. This is very important point, because soil is not permanently structured, it is not permanently located, its location keeps on changing because of ground movements, because of many other reasons that are still unclear. Therefore, I think professionally much attention should be given to properties of soil, behavior or conduct of soil, particularly by engineers, because it is basically engineer subject. Basically, though it is subject of geologists, indeed, because engineer itself is some part of geology. Engineers must know. Otherwise, I will not call that engineer. To be frankly, that without having soil knowledge, I'm not saying you must be master or doctorate in that. You must have some knowledge of soil, informative, applicable knowledge that can be applied to fields. You must have that. And because soil is not alone, it is linked to geology. So we must have some engineering application knowledge of geology, geology. That subject is not like theory of structure or designs of structures. That is different word. Of course, that is very difficult. The terminology is very difficult in all chapters of geology. But terminology is based on many properties of soil, or locations where soil is sometimes. But if I understand as a civil engineer, you can say working knowledge of geology or applied geology and soil, I think I would be in a better position to deliver a foundation which you call substructure, then if I just depend on some other's interpretation or some others telling me you do this for foundation, so I would do that because I've been recommended, but it is better if I understand myself. I have gone through many soil reports in my career, and that's my good luck, I can say. I would thank that because I was not very much qualified education wise. I'm very small person having first degree of engineering. I cannot call myself, high profile engineer in that sense where academic is valued. But I consider that academic is one part of engineering education, but you can learn a lot in field if you get opportunity and you get access to practical documents, reported documents, not text documents only, or academics based document. If you can have access to those and you have time and you devote that time to reading those and understanding those, I think you can better grasp real knowledge, not school knowledge or university knowledge. Because there was no one to explain to you what is that, and you have to decide yourself what actions you will do, how you will implement that. So I think that's a better education than university. And if you do this or you involve, say you study 4 or 5 big soil reports, soil investigation reports on various projects, I think you will have thorough understanding about what soil is. No need to go to subjects and go to university to get a degree to understand that, because already you understand that. This is my understanding. Maybe I am wrong, I can't say, because people mind something when I say this. I know people think he is criticizing degrees. In fact, I am not criticizing degrees. I just tell whatever happens in field that goes to university. It's otherwise. Means nothing comes to field from university, to be very frank. University is a follower in engineering, not leader. And I should therefore say that those engineers who have opportunity, who think that they are having opportunity, they must, even design engineers they must get copy of those reports. Field people get copies of those reports. Professional laboratories, I mean to say, their reports. I'm not saying individual based reports. Laboratories, material testing laboratories do conduct soil investigation, because it's a material testing in soil is a material. That point we should understand. As we try to understand every material, we try to understand, we have to understand soil in same way. Just like our own production material, concrete, we understand, we say this is concrete technology. Similarly, we have to spend our energies on philosophy of science and of soil. I should say science of soil, because it is big science, and unfortunately, I should say, people do not have interest in knowing about soil, because it doesn't have that type of applications as structural engineers in civil engineers like to have numericals, to have just data and apply formula and get answer. It's not that. Here, formula are very limited, but tests are dominant in material testing world. So soil, the word is very small and is ignored, but when you ignore soil, you ignore your structure. Simple answer is that. Soil plus foundation, you can say, just like we say in machine designs, soil must be considered when you design foundation. Soil must be taken as a part of foundation, as a dissipating force is part of foundation. Foundations can't take any force, we all know. Foundations are considered medium to transfer loads to underneath strata of soil, which further dissipates it further down, and then that force is gone there forever, like electrical earthing. So you can say soil is earthing world. Soil is unknown, to be very frank. Soil is unknown. Even you study soil reports, soil investigation reports, yet no one can guarantee what report says is exactly right. That's also assumptive, presumptive, and based on certain understanding, certain interpretation. Otherwise, that can also not be understood very well. There are certain points which are very normal in soil. Just we say density of soil, for example, which is also not uniform density, or you can say angle of repose varies from every soil, and also shear strength, bearing pressure of soil, that is, you can say, dominating factor for granule soils. And before that we can say other properties are here: water content, moisture content, or no moisture content, or value of N of certain soils. Then you can say RQD, which is rock quality designation. Then recovery of cores, percentage recovery of cores. And there are so many properties which we use: compaction, application of compaction, you can say, application of consolidation or natural consolidation. Then densification, you can say air expulsion. Means so much is there, but not very extensive, because soil is still in development stage. 100% nobody can say anything, and because it's beyond control of human being, water movement in soil, soil densification, consolidation, soil restructuring, chemical composition of soil at one point, one location, and then at other location, and then availability of water reservoirs below soil in stratas, different stratas. There are so many, and flow of water from one place to other place within soil, which you do not know. Capillary action, permeability action, porosity. There are various properties of soil which are very important from each and every engineer's point of view. We should understand that. If we cannot understand, then we miss something. Of course, I can't say you miss everything, but we miss something which we should not miss if you want to be good engineer. I mean to say, every engineer is good, but still I say that there are many chapters, preliminary you can say, which we study in engineering, and those are it is like engineering properties of soil and sample testing. Sample testing is very long, very vast. I'm not interested in about testing here, because testing is exclusively different world. At least we should know properties of soil. Even if you are not going to publish any soil report, you must understand what is soil, how does it work for you. If you say you are not designing foundation, even then it doesn't matter. You should understand, and you are doing work on site, means then it's a must for you. It's a must for you, because you can't depend upon what is told by someone or recommended by someone, because you are that report is located at one place. Maybe you are having 5 bore loads, 10 bore loads for a very big project, but you are working on real world, on real site where that bore load doesn't apply. Though we assume that this may apply, but could be it does not apply. So you are on site, you are in real world, you can say you are exposed to facts. Yes, there are different slides. So Engineering properties of soil, then we can say, soil classification and its structure, then capillarity and permeability, and then seepage forces and flow nets. Then compaction is one complete word, and followed by consolidation, which is, you can say, a kind of natural compaction. Natural compaction. This compaction was not natural, that is natural solidification of that soil body. Then shear strength of soil, and after it is earth pressure, which applies particular to retaining walls, and stability of slopes, and then pavement designs, pavement because pavement rests on soil, and soil stabilization. Then site investigations, subsoil exploration, which is basics, which is root of soil report, and bearing capacity, stress distribution, various types of foundations which come to application of soil, and then settlement of foundations and machine foundations. These are preliminary, you can say, chapters, but these cover total soil cases, total soil. If you have that much knowledge in clear terms, I think you can make better civil engineer or better field engineer, better design engineer, whatever you can say. Do not link it to what is your educational qualification, because if you are qualified, you can understand this. Knowing this much would work in better way rather than not. This is part of your engineering. Maybe sometimes it was not, maybe long back it was not part of engineering, or maybe of higher education, but I qualified this in my degree. And not only this is only soil I qualified, also applied geology. So I found that I didn't find a difficulty when I got such reports. Such reports when I got from laboratories on various projects, I had no difficulty in grasping those reports. So I enjoyed, because of course, some data you understand in field only, now you can't understand in university. But I felt that of course it was detailed one, not as given in books. So you are also not young then, you are also grown up. So your mind has learned many things without books. And I can say I got additional information from those reports, and in calculated way, in detailed way, not as I could get from books. Books are having limited pages, and therefore books can't be used for giving descriptive details, even except as if it is master's, people say master's degree or doctor's degree, that is different case. But information which you get and you interpret that, understand that without any problem, you can use it also in a better way. And application of that information is, if used, is successful, you are using that report, that point must be welcomed. And there are some people I have seen, oh, this is soil report, what shall I do? Okay, give it to some expert. And I don't know who that expert is. If I say, why are you giving to some expert to understand? Oh, it's not my subject, I'm a soil engineer. What sort of engineer you are then? What engineer you are? I am design engineer. If you are design engineer, then it's first responsibility to understand that. It's your first priority responsibility. It's your priority to know soil. Otherwise, you can't design foundations. And if you design foundations without its involvement, your design is no design. Your design is no design in that case. At least foundation design, I'm not talking of other structures. This is very important. And only because of this absence of use of this information, you'll find problems in buildings, in structures. That is sole reason that we should respect this. Doesn't matter if we have to go back to read first book, or doesn't mind. I don't mind, and one should not mind that. It means you have to read, alphabet of soil. Doesn't mean bad. I do. Because once I am out of university, I have a right to study every page of my syllabus again and again. I can't close box and say my job is over, my education is over. No. That was test only. You just passed some examination. It doesn't mean that you know it thoroughly. Remove from your mind dirt. And I was so brilliant, that I was so intelligent, I qualified those papers in one go, or I got some medal in that, or I was a student of merit. Forget all that. That was student life. Only life for student. And at that time you thought it's big. That quantity which you thought that big is no more big, because you have responsibility now. That time you did not have any responsibility. Your responsibility was just to study and pass examination, not even to be clear about what you learned. Had you been clear, then you must have got 100% marks, and you did get only sometimes 50%, 60%, 70%. And that are also on examination papers. You may be fortunate enough that you get questions which you studied. You can't study every question in examination times. So that was student life, which marked you graduate or postgraduate or doctor. But that's not professional life. Professional life is different, very different. Professional life means you have to deliver, certainly deliver. Otherwise, you cannot be called a professional if you are not able to deliver. That is very important point everybody must realize. I am just trying to speak this to clarify to everybody. Be clear that you were a student at that time, and now you are not a student. You are working for someone, some project, some structure, and that is your responsibility as first engineer, design engineer. And then it's the responsibility of person who constructs that, or you can say construction engineer. It's your responsibility, both your responsibility, that both must understand that report. And if you don't understand that report, then you cannot design, and that person cannot do that job on site, because that person is not explicitly clear of what is given in report. And it's not very complicated report theory, report text I'm not talking of. I'm talking of interpretation of technical report, which may be sometimes not very clear. There may be many options, and that causes a problem. So you must have a decisive power. You must generate a decisive power as engineer to make a decision out of many options, and which decision you find best must be supported by some explanation. What was reason that you opted for that? Everybody does structural analysis and structural designs. Those are bigger part. Foundation design is sometimes that makes engineers nervous. It happens. People, because this is responsibility, first responsibility. Yes, there is superstructure responsibility, I agree. Wind forces, other forces are here, but those forces are not that big. Your structure is at risk. But here, structure is at risk. We have to keep this in mind. Yesterday or other time I talked about some definitions, some explanations of engineering properties of soil, like clay-based soils, like minerals, soil minerals, clay soil minerals, or you may say cohesive soil minerals. We call cohesive soils, then we call granular soils, and we have many other terminology, many other definitions in terminology. So I talked of adverbal limits, which is also linked to cohesive soils, because clay and silt are normally termed cohesive and not granular soils, and there are in between both. We talked of structures of these soils, silt and clay. What are their structures? According to understanding based on crystallography, what is their thickness of members and angstrom, and also we tried to know how this liquid state, plastic state, semi-solid state and solid state are defined in these cohesive soils, which is most important point. You may say we extract out from that based on Atterbach's conclusions that this is your liquid limit, this is your plastic limit, this is your plasticity index, all that. Plastic is plastic limit, solid state limit, state solid limit, liquid limit, that we try to understand. And structures of these soil particles, gypsite with, tetrahedral with octahedral units concentration, in electronic world of soil, aluminum, magnesium, others they place. These are very terms which are not pleasing, but for understanding structure of soil, these are very much important. Very much important. If you could understand them, I think it would be better for everybody, because most dangerous soils are, you used to say, black cotton soil, or you indirectly can say equivalent to clay soil, because it contains more than 45% of clay. Always dangers lies in foundations, and engineers are not so definitive in that. What happens if they take risk of soil properties, and there is no formally available soil report, and without doing real testing of materials extracted from soil, from site, by drilling of boreholes, or by plate load bearing tests, some other results, and soil resistivity, electrical resistivity, thermal resistivity, and many more prime tests that are required to be conducted. And every house owner would not prefer this, because for them it's not easy to read, and that they cannot say they got what they wanted. They cannot understand all these results until you are educated one in that field, and that you are engineer, or you may deal in some other field where geology or this. So my dear friends, I would say I'm talking at length about this because I think it's very important. Time is no important here. Importance is if you grasp what soil is. To be very frank, soil is nothing in fact. To be very frank, as we say, soil is soil. It's rubbish. Yeah, what is talk? You're sitting in soil. Don't you feel very happy? You're sitting there. Yes, soil. Same soil conducts its strength in thunderstorm. Same soil works along with water in air. Don't forget that. When it blows, what happens? Silt particles, clay particles, they suspend in air for hours. What do you call that? So soil depends, soil has properties which you can understand only when you understand what is soil. That was my, original thought without any text reference. First you have to think, that's what I say, thinking is last or only result in engineering. And that without thinking, engineering doesn't exist, remember. If you just read books and say, I have understood, then I think you are not well understood. You are not well understood. You are only boasting that you are. Reading, from point of reading, I am not saying that. Reading books from point of understanding, I am saying that. Books you can read like novel, it doesn't give anything. If it is not novel. If it is novel, okay, you can enjoy that. It's nothing to do with engineering. Engineering means you have to live. Simple. You have to live. Your doctor is your additional doctor in your life is engineering or engineer who provides you structure, house, everything. Let me take some water. We talk continuously because I feel some water is important to take to keep myself lubricated the throat, because studies goes on, and thinking is also important meanwhile. Thinking is also important. And still water is hot, so I want to take some water. Otherwise, even in thermos, it will reduce its temperature. After some time, still maybe something good here. As I said yesterday, and you all know what we did. We talked of black cotton soil and stabilization of soil, and we discussed about percentages of various compositions, various properties in this black cotton soil, which is very good from engineering understanding. As we stay, I still remind you that what we did in black cotton soil, it was composition like this. Means clay is 42 to 72%. The major portion in black cotton soil is clay, which is followed by silt, that's up to from 15 to 30%, and fine sand, which was 2 to 29%. Fine sand, fine sand, and that is like coarse sand is 1 to 7%, so coarse sand is minimum. And also, if you go to Atterbuck limits, liquid limit is 45 to 100%, plastic limit is 15 to 40%, and then plasticity index is 20 to 60%, and shrinkage limit is 9 to 14%. what is this person? First of all, you have to ask a question yourself. Maybe you understand, many of you understand that. Yet, just for refreshing, this person is a what? Person is a water in soil. Quantity of water in that soil is percentages. When you can say liquid limit, as we state, 45 to 100%. If you put liquid limit is, it means literally it means it stays where. Liquid limit means where if you add more water to that limit, your soil water becomes a fluid flowing, it's a flowing fluid. Laminar flow, you can say, not exactly turbulent. I'm talking of laminar flow. Means it can move from one location to other location. That's called liquid limit. Your liquid limit plus it is, and if you take liquid limit minus, then this means you are withdrawing water from that liquid, and when you withdraw water content, this means it evaporates its water, or that water content goes drying for hours, and when you get heated up, you can take that water percentage in various considerations. So when you say liquid limit, means little addition to water converts to liquid, and little withdrawal of water from that starts gaining shear strength. Because at that point where liquid limit starts, there is no shear strength, and if you bring down water content, it shall start working on its strength. That is called, if you withdraw some water, you'll get plastic limit, because at that time this comes one liquid limit and then plastic limit. And you can say, in plasticity index, I told you, so there is liquid limit, there is plastic limit, then there is semi-solid, and there is solid limit. Means it's like something we discussed, because these are very important. We also discussed about stabilization of expensive soil, and also one more point here is buildings affected by clay. Means how buildings stand on clay and disturbed. We said that hogging of buildings an important mode of conduct of black carbon soil. Means when a structure of traditional unreinforced brick masonry is subject to hogging, this is not RCC talking about ordinary buildings, cracking due to direct tensile strain in bending is likely to occur at a very low value of delta over L. Delta over L is defined here. Then stabilization of soil, and then all methods are given there. I did not study yesterday about underlying pile which was there given as let us just read it for 2-3 minutes and understand. It says that underlying pile foundations originally developed in Texas in USA under CBRI has done considerable work on design and development of this foundation in black carbon soil area. Such type of foundation appears to be a good solution to foundation problems of expensive soil. Underlying principle of pile and beam construction is to support superstructure of building over beams which are clear of ground surface. And span span over piles, span over piles which are anchored at a depth where soil has nearly stable water content during various seasons of year. Thus, thus, you know, it shall be free from appreciable seasonal movement. Now, black cotton soil has depth has found up to 3.65 meter, 3.67 meter, and also let me gas down. No problem. Hence, length of under rim piles is capped up to 3.65 meter in deep deposits of black cotton soil. In shallow rock deposits, the pile is carried down into non-expensive layer to a depth of at least 0.6 meter. Many spacing of piles depend upon load bearing capacity and plan of building. However, spacing may be varied. That is 1.6 meters to 3 meters. Piles should be provided under every wall junction in plan of building so that point load on cement beam can be avoided. Bearing capacity of an underrim pile is sum of total skin friction, resistance, and upon. Pile should be provided spacing ranging from 1.5 to 3 meters. Pile should be provided under every wall junction in plan of building so that point load on cement beam can be avoided. Bearing capacity of underrim pile is sum of total skin frictional resistance and total point resistance. Well, bearing capacity of underrim piles is sum of total skin frictional resistance and total point resistance. Now what you say a pile functions as column. Pile functions as column when soil shrinks away from stem in still. So when we say it's considered column, it is a shrinkage and now I'm not going to bending moment or all that in this, but that you know all. That's not my purpose to talk of in this elementary talks. This was actually, chapter name was Expensive Soil. Then we have to understand there are various types of foundations also which you know well. We'll take up that one, but here immediately I'm not going to do that because of many reasons, and I want just to concentrate on something. We have gone through soil stabilization as well in details, but now consolidation and compaction. Yes, now we are talking of something related to compaction. As we discussed yesterday about compaction. It's a big item. Compaction means it's part of backfill. We can say compaction part of backfill as well as part of natural fill, natural state. Now, what's actually compaction? We know, we discussed yesterday. What is compaction? We'll talk little in explanation of that. What is compaction? I'm not able to comfortably sit due to what reason I don't understand. No, I need light on book also, but I'm reading. Let us see what is, we know compaction, what compaction is. What are factors that affect compaction? Now, theory of compaction. A principle of compaction can be explained as like, Lambe did, and Lambe what did, and what Hodge and Togler lubrication theory. Let us see. There is Lambe's physical, a chemical theory, and Hodge and Togler's lubrication theory. Sorry. I got seepage. How I got seepage? I don't know. Yes, it's there. Exercise Lambe's theory, Lambe's physico-chemical theory. Each particle of soil has got a thin layer of solid adsorbed water. Each particle of soil has got a thin layer. This particle talking, I'm not talking about layer of particle of, I'm not talking of layer of soil, but particle. It says that each particle of soil has a thin layer of solid adsorbed water. Solid means particle itself, absorb water, and thick layer of viscous double layer water. Got it? Each particle of soil has got a thin layer of solid, adsorb water, and under and thick under water, thick layer of viscous double layer water. Increase of moisture content of soil increases thickness of viscous double layer water. With increase in thickness of point to understand. Each particle has a thin layer of adsorbed water and thick layer of viscous double layer water. Increase of moisture content of soil increases thickness of viscous double layer water, and with increase in thickness of viscous double layer water, viscosity of water, increase in thickness of viscous double layer water, viscosity of water, surface tension forces, and water soaking porosity, etc. As a result of arrangement of particles, is easier with great water content, and then dry says as a result of arrangement of particles are easier with greater water content, and hence dry density increases. But increase in dry increase is only up to certain limit. It's up to optimum moisture content, beyond which it is not possible to remove air to the air by decreasing void space. That's what says. It's something, sometimes it's very unpleasant subject, because it's sleeping, when you study like this, you feel drowsy, because there is no interesting material in that. No formula, no numerical, just read and understand, and then see on site what you do. So both are tedious. Okay. So, we go professionally. Okay, let me read it so that you can also listen what I'm reading. I have read it, but I'm just reading for repetition. That's a must. We will talk testing later on. Now understanding should be clear for what we understand in field. According to this theory, particle of soil has got a thin layer of soil adsorb water and thick layer of viscous double layer water. Increase of moisture, increase of moisture content of soil. Increase of moisture content of soil increases thickness of viscous liquid, viscous double layer water. Now, with increase in thickness of viscous double layer water, viscosity of water, surface tension forces, and water soaking capacity decreases. Water soaking capacity decreases. Content and hence the dry density increases. say, as a result of arrangement of particle is easier as a result of as a result of the arrangement of particles is easier with greater water content and dry density increases. But this increases only up to certain limit, that is up to optimum moisture content, beyond which it's not possible to remove air by decreasing void space. This is Lambe's physico-chemical theory. Now, Hagen-Togler, what we call it, Hagen-Togler's lubrication theory. According to this, it's assumed that soil particles absorb a film of water. Soil particles absorb a film of water when water is added to dry soil. Because this theory, it's assumed that soil particles absorb a film of water when water is added to dry soil. So what happens? Soil particle absorb a film of water when water is added to dry soil. Now when you addition of more water, this film get thicker and permit, soil particles to slide over each other. More and more thick means particles can slide on each other easily. This process is called lubrication. This is lubrication of soil. Means these particles slide over each other when more water is added to soil. Since thickness of water film in a coarse particle is negligible, on a coarse particle cannot retain, so thickness of film on coarse particle is negligible in comparison with particle diameter. Lubrication effects are limited to fine-grained soils. Because of lubrication, addition of a small amount of water to a dry soil adds compaction process. Addition of small amount of water to a dry soil adds compaction. It's a compaction process. Additional water replaces air from soil. This additional water replaces air from soil voids. Soil voids up to a certain point, but after a relatively high degree of saturation is reached, water occupies space which could be filled with soil particles, and amount of entrapped air remains essentially constant. There is therefore an optimum amount of moisture content or moisture water for a given soil, and compaction process which give a maximum weight of soil per unit volume. This is a small paragraph, but very important to understand what we are talking of. What we say lubrication process. If you add water to soil particles, and these particles get more and more double layer, says that according to this, assume that soil particles absorb a film of water where water is added to dry soil. That soil, you add water to that one, and when you add more water, these films get thicker and permit soil particles to slide over earth more easily. This is called lubrication. This is called lubrication. Process is called lubrication. And since thickness of water film of coarse particle is negligible, coarse particle I am talking, since thickness of the water film on a coarse particle is negligible in comparison with particle diameter, lubrication effects are limited to fine grained soils and not casted soils. Because of lubrication, addition of small amount of water to a dry soil aids compaction process. Additional water replaces air. Additional water replaces air. Additional water replaces air from soil. From soil voids up to a certain point. But after a relatively high degree of saturation, is raised, water occupies space which could be filled with soil particles, and amount of entrapped air remains essentially constant. There is therefore an optimum amount of mixing water for a given soil and compaction process, which give a maximum weight of soil per unit volume. Now we have certain factors that affect process of compaction, because this is nothing but process of compaction we are talking. When we say this lubrication process, lubrication is a part of compaction. Now it is moisture content which is very important here. Factors affecting compaction, that is moisture content. Moisture content. Compacting effort. This is compacting effort. Soil type, method of compaction. So these are factors that affect compaction, and these are process of compaction. Moisture content. Let me put fan on. Versus moisture content. Mixing of water to dry soil. Mixing of water to dry soil helps in bringing solid soil particles together. Mixing of water to dry soil helps in bringing solid soil particles together. Actually, water coats soil particles. Water coats soil particles at low moisture. At low moisture, soil is stiff. When moisture content of particle is low, soil is stiff and cannot be packed easily. With increase in moisture content, water starts acting as lubricant, and hence soil particles come close due to increased workability. Thus soil water air mixture starts occupying lesser volume under compacting energy. Dry density increases due to reduction in volume. As more and more water is added, a stage is reached when air content of soil attains minimum volume under particular compacting effort. Dry density at this stage is maximum, and this particular moisture content is known as optimum moisture content. An addition of more water reduces dry density because extra water occupies space which soil would have occupied. This is moisture content effect on soil. I read again because this is actually deciding factor of compaction and dry density. Mixing of water to dry soil helps in bringing solid soil particles together. Actually, water coats soil particles. At low moisture, soil is stiff and cannot be packed easily. With increase in moisture content, water starts acting as lubricant and hence soil particles come close due to increased workability. Thus soil water air mixture starts occupying lesser volume. Under compacting energy, dry density increases due to reduction in volume. As more and more water is added, soil is reached when air content of soil attains maximum volume under particular compacting effort. Dry density at that moisture content is maximum, and this particular moisture content is known as optimum moisture content. Addition of more water reduces dry density, and because extra water occupies space which soil would have occupied. So now here is one graph which is for compacting effort, and we'll talk of compacting effort. What is compacting effort? How it affects compacting effort. If compacting energy is increased, and say it's increased, value of maximum dry density increases, and value of optimum moisture content increases. A set of typical curve for dry density moisture content exists. Just shown in P. I'll show you. 3 compacting efforts were applied. Three compacting efforts were applied, that is 15 blows, 20 blows and 25 blows, and results were given, plotted. Value of optimum moisture content in all 3 cases have been shown. Now point A, B and C are there. I will show you that one. From curve it is clear that curve shifts upwards and left direction due to increase in compacting effort. The value of optimum moisture content increases. Says that value of optimum moisture content decreases. Wait a minute. From curve it is clear that curve shifts upwards and left direction due to increase in compacting effort. Value of optimum moisture content decreases, and value of dry density increases. increases with increasing number of blows. Line joining peaks of all curves. Line joining peaks of all curves is called line of Optimus. Line of Optimus. Shape of line of Optimus is more or less like zero air white ratio. White line. Of course, there is no linear relationship in increase in maximum dry density with increasing compacting energy for a given soil. Limit is also reached so far as achievement of maximum dry density is concerned, beyond which no amount of compacting energy increases its volume. So let's now see what actually it talked of. That's what it's saying. There's a diagram here, curve here. You can just look at that. What's that? What do I say? Oh, sorry, this is that curve, you see. There are three curves for different loadings, different blows, and x-axis is percentage moisture. I think it is moisture content, and vertical is dry density. So horizontal is moisture content, and this axis are and all units. So vertical y-axis is dry density, and this axis size, you can see moisture content, and three curves A, B, and C. A says that there are 20, I think 10 blows, 15 blows, 25 like that, right? 15, 20 and 25. 15, 20 and 25 blows, and this is that curve. And there's a peak if you join A, B, C, Z, how you join them, and if you see this curve, that is, this curve is zero air wide line. Zero air wide line is the ideal condition. This is there. You can say this is indicator 1, but this tells what we are talking of. Now we have understood what is compaction and how it works. Lubrication based compaction, lubrication by water, and blows by force. Now we say maximum dry density depends upon type of soil. That's also very important. Types of soil. Well graded coarse soils can be compacted to a very high density as compared to fine grained soil. Heavy clays can be compacted to low densities. Heavy clays. Optimum moisture content of grain soils is more as compared to coarse grain soils. Optimum moisture content of grain soils is more as compared to coarse grain soils. And then optimum moisture content grain is more as compared to coarse grain soil. Optimum moisture content of fine grained soil is more as compared to coarse grained soil. Addition of every small amount of fines to coarse grained soils permits development of higher density, which increases moisture content for same applied energy. Large amount of fines decrease maximum. Large amount of fines decrease maximum density and increase OMC, optimum. Then we go to, after that, large amount of fines decrease, large amount of fines decrease maximum density and increase optimum moisture content, and hence only optimum amount of fines should be added to coarse grained soils. A well-graded soil having a large coefficient of uniformity would have a much higher compaction. Then a large coefficient of uniformity will have a much graded wall. A well-graded soil have a large coefficient of uniformity shall have a much higher compaction. This is clear from fact that with the decrease in plasticity, soil becomes plastic at a lesser value content and hence for soil found that plasticity efficiency of a coefficient of uniformity in general, it has been found that plasticity decreases, compaction increases. This is clear from fact that with decrease in plasticity, soil becomes plastic at lesser water content and increase for equal amount of water content, particles can mostly be rearranged. Method of compaction. Manner in which a compaction is done, or you can say compaction done, or compactive energy is applied, influences attainment of dry density. Very little known as to how and why method of compaction influences density. Weight of equipment, manner of opposition. Influence of value of maximum dry density in the soil. Effect of compaction on properties of soil. Now, let's say effect of compaction property of soil. Compaction has great influence on different properties of soil. Mainly properties are influenced by compaction are now compaction on structure, effect of compaction on structure, effect of compaction on compressibility, and effect of compaction on solubility and shrinkage and pore pressure. Now you should get smart, at least to understand what you are talking. And let me just see sky 1 minute please. I am concerned about weather very much. Let me see how it works. Okay, we go fast then. Now, what I'm talking is effect of compaction on properties of soil. Compaction has influence on different properties of soil. Mainly following properties are influenced by compaction. Effect on structure, which is structure, soil structure. Effect on permeability, effect on compressibility, effect on swellability and shrinkage, effect on pore pressure, effect on shear strength and stress strain characteristics. So how many effects are here? Structure, soil structure. Permeability, what is permeability? Soil structure we have studied in minerals. What type of this is? You can say gibbsite with tetrahedral with octahedral. Then their combination, then soil structure, single pointed structure of each particles, and then clubbing particles, and then same structure, structure like this, then honeycomb structures in both cases. Like, and then one plate structure, platelets is different kind of platelets and flatted plates that we have. That's that structure of soil. So compaction affects that structure. Then it affects permeability. Permeability, that allows water flow through its structure, through its voids. That's permeability. And compressibility means how much soil can be compressed to increase its density. And swellability and shrinkage, how much this compression help in, decrease swelling and shrinkage. Then on pore pressure means lesser voids would decrease pore pressure. And effect of compression on shear strength and stress strain characteristics. Now, effect on compaction of structure. Structure of compacted soil. Why this unnecessary? Structure of compacted soil is dependent upon a number of factors. The structure of a compacted soil is dependent on a number of factors, such as type of soil molding, water content, and type and amount of compaction. Coarse grained soils having very little or no fines continues to possess single grained structure. What it says? Says coarse grained soil having very little or no fines. Coarse grained soil with no fines, you can say, or little fines, continues to possess single grain structure at whatever white ratio or water content. We have to be slow sometime. So what you say, single grain structure it is, if there is no fine in that, or when it is fine, continue to possess single grain structure. We studied yesterday. At any void ratio or water content, that is possible that this structure. At any void ratio or water content, says coarse grained soils having very little or no fines continue to possess single grain structure at the void ratio or water content. When plastic goes. When plastic fines are only just sufficient to fill voids of coarse grained soils, coarse grained skeleton structure is formed. When plastic fines are only just sufficient to fill voids of coarse grained soils, the skeletal structure is formed after compaction. When coarse particles do not touch or one another. In case of fine grained soils, just I think it's little light coming up. That will do my job for crows. Because crows are hungry, probably. This crow will be hungry. That we don't have food. Sorry, is waiting. Waiting for me for their food, and I give them their food. Oh my God, this page is gone. It's missed. Oh, it's gone somewhere. Really left away, gone away. Don't cheat me. Don't cheat me. Yes. So I said, when plastic fines are only just sufficient to fill voids of coarse-grained soils, coarse-grained skeleton structure is formed after compaction. When coarse particles do not touch one another, but float in compacted matrix of clay, then cohesive matrix structure is formed after compaction. So this is effects on structure I am talking. I have to talk of effects on structure, effects on permeability, effects on compressibility, effects on swellability and shrinkage, effects on pore pressure, and effects of compaction on shear strength and stress strain characteristics. We already talked about moisture content curve. Depending on blows, how moisture content is related to dry density and how zero air void line works. So we are talking of effect of compaction on structure. This is the first effect, but this is on a structure. Be careful. This is not ordinary. Effect of structure means the structure is being affected, and that's where we should be very careful. The structure of, I am repeating that, structure of structure of compacted soil is dependent upon number of factors such as type of soil, molting, water content, and type of compaction. Coarse-grained structure, coarse-grained soil having very little or no fines continues to possess single-grained structure at whatever void ratio or water content. When plastic fines are only just sufficient to fill voids of coarse-grained soils, coarse-grained skeleton structure is formed. After compaction, it is formed. When coarse particles do not touch one another but float in a compacted matrix of clay, then cohesive matrix structure is formed after compaction. We have studied this in structure of soil. We studied yesterday in other talk. In case of fine-grained soils, presence of clay complicates whole show. Lambe conceived an idea which was further modified by Syed and Chan. According to it, at low water contents, adsorbed water layer does not develop fully, which leads to low interparticle repulsion, and hence such compacted soil mass have a tendency to possess flocculated structure. Flocculated structure, we say that. We studied our structure. An increased water content expands adsorbed water layer, increases interparticle repulsion, and tends to develop higher pressure due to compacting pressure. Due to this great shear strain, great shear strain is produced during compaction, and hence such soil mass has a tendency to possess dispersed structure. It has been seen that dry site compacted clay and undisturbed clay tend to have flocculated type structure, and wet site compacted clay and remolded clay tend to have dispersed type structure. Got it? Same structure we are talking, but for during compaction. Here we talked for subvector on structure, that was for coarse grain. Now we are talking how it conducts on fine grain. Both are there, coarse grain and fine grain. In coarse grain we have concluded that mixtures of clay, and then we talk this structure of compact soils dependent upon number of factors such as type of soil. So we say case of fine grained soils, presence of clay complicates the whole issue, and according to low water contents, adsorb water layer does not develop fully, which can lead to low interparticle repulsion and hence such compared to soil mass having a tendency to possess flocculated structure, not dispersed one. An increased water content expands adsorb water layer, increases interparticle repulsion forces, and can develop higher pressure due to compaction pressure. An increased water content extends adsorbed water layer, increases interparticle repulsion, and tends to develop higher pressure due to increased interparticle and increased water content expands adsorbed water layer, increases interparticle repulsion, and tends to develop higher pressure due to compaction and due to compacting pressure. Due to this, greater shear strain is produced during compaction, and as such soil mass has a tendency to possess dispersed structure. It has been seen that dry site compacted clay and undisturbed clay tend to have flocculated type structure, and wet site compacted clay and remolded clay tend to have dispersed type structure. Effects of compaction on permeability. Permeability decreases. Permeability is when water flows through voids of soil, it successfully flows through that. We call that property permeability of soil. Permeability decreases with increase in dry density. You are getting dry density higher, means you are reducing voids in that and soil structure, and when voids are reduced, water shall flow only to that extent. Permeability decreases with increase in dry density. Increase in dry density. If you increase dry density, certainly voids will reduce, and when reduction of void means reduction in routes to water flow, so permeability is reduced. For given void ratio, larger size of individual pores, greater is permeability. Larger size of individual pores, greater is permeability. Minimum permeability occurs at or slightly above optimum moisture content, after which a slight increase or permeability occurs. There is now got it. Permeability relates to volume of voids. So minimum permeability occurs at or slightly above optimum moisture content, after which a slight increase in permeability occurs. There is sharp decrease in permeability with increase in molding water content on dry side of optimum moisture content. This is permeability. It decreases when increase in dry density. Okay, there is sharp decrease in permeability with increase in molding water content on dry soil side. Effect of compaction on compressibility. A wet site compacted soil is more compressible than a dry site. Compacted soil at low pressure range, if both are having same void ratio. Initially saturated. At high pressure range, dry site compacted soil is more compressible than wet soil. Now we are talking about swellability and shrinkage. Swellability and shrinkage. Swellability. Dry site compaction soil swells more when dry site compaction soils swell more when given access to moisture. Then to wet site compacted soil. No problem, let it be yawning. What to do? What is what? Dry site compaction soil swells more when given access to moisture than a wet site compacted soil. A soil compacted wet of optimum will shrink more on drying than soil at same dry density of optimum. So effect of now shear strength and strain stress strain characteristics. Increased compaction. Increased compaction efforts due to optimum results. Efforts dry increased compactive efforts dry of optimum results in an increase of strength in clay. Increased compactive efforts wet of optimum may result in gain or loss of strength, but effect is very little. For same compacting energy and compacted density. Got it. Increased compacting effort dry of optimum results in an increase of strength in clay. Increased compactive effort wet of optimum may result in gain or loss of strength, but effect is very little. For same compacting energy and compacted density, dry side compaction gives higher strength, let's say, than wet side compaction. Saturated samples of clay compared with compacted dry. Saturated samples of clay compacted dry of optimum has low pore pressure at low strains and in underdrained shear of but at high temperature. So saturated samples of clay compared dry of optimum has low pore pressure at low strains in undrained shear strength, but at high strains all types of compacted soils exhibit same pore pressure. Dry side compacted soils produce much steeper stress strain curve and develop maximum strength at low strains. Now, once again, I read this and I go to compaction and field. That's very important. Paul is a very lazy, you can say, drowsy, all time toiling. Actually, very boring. That's why I think engineers do not like this subject. It's fact. Maybe this is one of reasons they ignore this. But again, I say ignorance would not work, because by ignoring this, you are ignoring your building. You are ignoring your building. out little more buttons so that I can get some air, It doesn't look nice, but humidity is 90%. What to do? You know that? 90% here. More than 2 hours is gone. So let me read again. It's better to read again and again. Effect of compaction on shear strength and stress strain characteristics. Increased compacting efforts. Dry of optimum results in an increase of shear strength, increase of strength in clay. Increased compacting effort wet of optimum may result in gain or loss of strength. But effect is very little for same compacting energy and compacted density. Dry side compaction gives higher strength than wet side compaction. Saturated assemblies of then now saying saturated samples of clay compacted dry of optimum as low pore pressure at low strains in undried shear depth, but higher strain all types of compacted soils exhibit same pore pressure. Dry side compacted soils produce much super stress strain curve and develop maximum strength at low strains. Compaction of soil. Compaction in field. Once value of optimum moisture content and corresponding maximum dry density is obtained in laboratory from proctor test. Field engineer tries to compact soil at dry density is obtained, moisture content, once value of optimum moisture content and corresponding maximum dry density is obtained in laboratory from proctor test. Field engineer a structure test that shows, field engineer tries to compact soil in field at OMC, that is optimize content, so that he gets maximum drive density, maximum drive density. Field engineer tries to connect soil, compact soil in a great field. Come on. No, I'm getting wind actually. That's more important. I was not getting here. So I little interested myself. Now this OMC says that field engineer tries to compact soil in field at OMC so that it gets maximum dry density obtained in laboratory or at least 95 to 98% of what we receive in laboratory, got in laboratory. 95 to 98%, depending upon certain fixed engineer criteria. Compaction in field can be done by different types of equipments. All types of equipments are not suitable for all soils. Essentially there are two types of soils. So what we do by many equipments, we use them in field, and that is, all types of equipments are not suitable for oil soils. There are two types of soils, sandy soils and clay soils. Now most effective method of compacting sandy soil is by vibration. Moist, medium and fine sand cannot be compacted by this method. Okay. So, most effective methods to compact sand soil by vibration. Most medium and fine sand cannot be compacted by this method because of what? Because of capillary forces, but when saturated these can be compacted, this can be compacted by process named vibrophloration. Called vibrophloration and compact. In this process, a vibrator needle having a self-contained method coarse, medium and fine sand cannot be compacted by this method because of capillary forces, but when saturated using in this process vibrator needle having a self-contained motor has two parts. Vibropollutation we call it, vibropollutation for fine soils. In this process a vibrator needle having a self-contained motor has two parts through which water can be discharged. Water is first made to discharge through lower part of vibrator. Vibrator is inserted into soil. When fully inserted, discharge through lower part is stopped and upper one is started. Vibrator is many times lifted and in seconds. Vibrator is many times lifted and inserted till desired compaction is attained. Is vibro filter. Vibro flotation is called. Clay soils cannot be compacted by vibration. Kneading type compaction is most effective method. Kneading, that is the names of equipment for different types of soils. So let us say hand temper, hard temper, there is 2.5 to 10 kilogram rammer we call it. It is for sandy soil suitable. It is for sandy soil suitable layer thickness 12 centimeter. For clay soil is unsuitable. Next number this is, and then this is there is a hard temper cell rammer of 10 kilogram. The pneumatic rammer 10 to 75 kilogram. Sandy soil suitable layer thickness 20 centimeter. And clay layer suitable layer thickness 15 centimeter. This pneumatic rammer 10 to 75 kilogram. Suitable thickness 20 centimeter for sandy soil and 15 centimeter for clay soil. Then you can say vibrators. Vibrators suitable for sandy soil and unsuitable for clay soil. Now let's go. Smooth wheel rollers. Smooth wheel rollers suitable layer thickness 20 in sandy soil and for clay it's not suitable. Sheep foot rollers unsuitable for sandy soil and suitable for clay soil of 20 centimeter thickness. Sheep foot rollers and pneumatic tired rollers, and this is suitable for sandy soil, unsuitable for clay soil. Then frog hammers suitable for sandy soil and less suitable. Then we can say frog was suitable for sandy soil. There was my book that's frog was suitable was suitable. Ram plates suitable. So how to compact? This is little one, not fully descriptive, little one. Then we go to selection of number of passes for rollers and field trial. This is a site experience, very important one from compaction viewpoint. So we should also understand this in its entirety rather than running away. Let us see how it works. You can say selection of number of passes for rollers and field trial. Majority of earthworks, different types of rollers are used for compaction. Number of passes which are to be given has to be determined in field by field trial. Correct thickness of number of passes which are to be given has to be determined in field by field trial. Correct thickness of embankment which can be compacted at a time and economical number of passes of a roller can be determined by following test in field. Test area about 20 meter long and 15 meter height is chosen. At actual site of construction, fill material from burrow pit is brought and spread over. This area is three steps. For this area in three steps. Each step having a width of 5 meters. Depth of loose materials in step may be kept different. Normally depth of normal depth is kept such that after compaction thickness of layer is from 15 to 25 centimeter. Water should be added to soil so that its water content is that of optimum moisture content. The sprinkling of water and mixing cannot be done either by machine or by other means. After that, water mixing can be done either by machine or by other means. After that, test is conducted by means of desired rollers. And mean dry density of full depth of each strip is found after 4, 6, 8, 10, 12, 14, 16, 18, 20 passes. Mean dry density is found after every, can say 4 and then followed by 2 gap 4, 6, 8, 10, 12, 14, 16, 18 passes, 20 passes. A graph between number of x-axis and dry density y-axis y-axis be drawn. A typical graph is shown, which will show you. From curve it is evident that drive density goes on increasing in initial stages, will increase in number of passes, but after some time increase in drive density is very small with increase in number of passes. In this case, one point is there, this point A. I'll show you that corresponds to 10 number of passes, which is most economical number of passes, and drive density obtained has been shown by another point in same coordinate. If it is desired to have still higher density, then heavier type of roller has to be used, because increase in number of passes will not be economical, and if one goes beyond critical point, then roller is only achieving an elastic deformation and rebound in soil surface. With a little experience in field, an engineer can decide number of passes required for weight and design of roller. So, wait a minute, let me repeat this. Before going that further, let us see what I'm talking of. This curve, which is very important one. This curve is very important one for everybody to understand. You know that, just look at that once again, so that you refresh your mind what you studied before. This is that curve of field test. You can see A point there, B point there. Drive density, this is indicating vertically on ordinate and abscissa x-axis. You can see number of passes, and it's written there. It is written there, in back 4, 6, 8, 10, 12, 14, 16, 18, 20, like that. And you see point A shown there up to where there is increase in density, and above that very little increase, and number of passes are there, but very increased. So you can say point A can be critical with point B giving density, achieved density of that. And it says that if you want to more, you have to use more powerful machine, and it can't depend upon other one. More power can give you better results. That's what it says. If you use more number of passes, or there was rebound and nothing else. Rebounded, so that on the economical, you can say, compaction. Now I will read it again once more. This I will not read the effect of compaction. We know that compaction affects on structure, it affects on permeability, it affects on compressibility, it affects on swellability and shrinkage, it affects on shear strength and stress, strength characteristics, and how compaction done in field. It's done at optimum moisture content, and it should be 95 to 98% minimum, depending upon criteria fixed by engineer. And this test can be done in field, and all types of equipments are installed, used, and then we have seen classes of soil, let's say based on let's say one, I'm talking equipment is there. Where is the equipment? Now we say we have rammer, you see, hard temper, which is from 2.5 to 10 kilogram. We can use it for compaction of sandy soil, and thickness to be compacted to 12 centimeter, that's from 15 down, 12. And for clay soil, we have to use something else, not this. Then there's another machine that's called pneumatic rammer. Pneumatic rammer, that is up to 10 to 75 kilogram for sandy soils, okay. Layers 20, and for clay soil, suitable layer up to 15 centimeter. Then there's vibrator, suitable for sandy soil, not suitable for unsuitable for this vibrators. And smooth wheeled roller. Smooth wheeled roller. This is suitable for thickness 20 centimeter down to. Then same smooth wheeled roller. Now we'll see then after this smooth wheeled roller, suitable for clay soil. Sandy soil is not for that one. This is a smooth wheeled roller, not so suitable. Then sheep is smooth wheeled roller, is smooth wheeled roller that is suitable there 20 centimeter in grain soils, and sheep foot roller that is unsuitable for sandy soil, suitable for this is. Then sheep foot roller, then pneumatic tire roller, suitable for sandy soil and suitable for clay soil. Oh yes. So we have seen selection of more classes. We'll repeat it later on, not now. I'm just going to do something on field control of compaction. It's just understanding, we're not going to conduct test. It's just field control of compaction. Field control of compaction. When compaction is being done, stay on it. What to do? Hold on. Let me change my style. Compaction test in field. Proctor needle. Proctor needle. So I can see if I keep proctor, this means that if I give some idea, my projector, so that I can take photographs of that. That is possible, but I have to be here like this somewhere or somewhere like that. Okay. Field compaction test. When compaction is being done in field by means of roller or other items or machines, it's necessary to measure dry density of soil as an inspection procedure to determine whether or not soil is being compacted to specified density. There are a number of methods available for making such measurements and thereby controlling moisture content and dry density. Rapid method of testing is necessary for effective control of density and moisture content during compaction. Hence only such methods are used for this purpose, which gives quick result. Oven drying method of determination of moisture content in laboratory is very slow. Rapid determination of compaction value of moisture content and dry density can be done by an instrument named Proctor's plasticity needle. Proctor's plasticity needle. R. Proctor discovered auxiliary device known as Proctor's plasticity needle to check moisture of content and density of compacted soil. Apparatus consists of needle attached to a spring loaded plunger. The stem of it is calibrated. To read a pounds or kilograms. Device is placed on surface of soil and is pressed a specified distance into it by manual pressure applied by means of handle and a calibrated spring which measures loads. Compression of spring indicates penetration. Compression of spring indicates penetration. Resistance, compression of spring indicates penetration. Resistance offered by soil. Sliding ring on stem. A sliding ring on stem indicates maximum penetration. Resistance obtained during test. Needle shank has graduations inscribed intervals to indicate depth of penetration. Needle has a number of tips of varying cross-sectional area, so that a wide range of penetration resistances can be offered. These tips are interchangeable and they have varying area of 0.05, 0.1, 0.05 square inches. Now to perform experiment person holds needle normal to surface and forces it into soil at a rate of approximately 12 mm per second. Reading should be taken when needle moves smoothly through soil at about this. Reading should be taken when needle moves smoothly through soil at about this rate without need of additional pressure. Continue until penetration reaches up to 2 inches or 50 mm. Read this pressure corresponding to sliding on stem. Take 3 or 4 readings and record their average and needle size. That gives penetration resistance in square inches, leaves per square inches. Now for a given soil, compacted according to standard procedure, there is definite relationship between penetration resistance and this relationship is determined for several moisture contents to develop core for that soil, and this moisture content and penetration resistance is plotted when moisture content at time of performing standard Proctor test. Dry density is found at various moisture contents at same time penetrating resistance for each. So I will show you this curve. You know this very well. It's still just for the memory. I will show you the fresh in your memory. This is your Proctor needle, very simple one. You can see here, Proctor needle. And we saw these two curves here, same purpose. First is penetration curve, and then as diagnostic curve. Dry density, this is first one graph was penetration resistance, and moisture content was taken as 6, 8, 10, 12, 14, 16 percentages, and then penetration resistance, and that starts 0 to 900 something, and then you can say at 10 percentages this is the same. And of course density you add from that curve moisture content and dry density. So there are so many other methods to find density. I'm going to that one now. My purpose is not experiments. My purpose is something else here. Now most important part in this. Another important part of our soil, which is, you can say, durability time, or you just like to say material, soil is durable. We call soil is durable. Also, in our terms, not in books terms. When I say the soil has been there for, let us say, when I say soil has been there for 50 years, or I don't know how many years, this ground is still there, or they have been, some structure here for so many years, or we demolish that, or you can say there is no disturbance to this soil portion for 5 decades, 6 decades, 7 decades. Means it was undeveloped area. Hardly fertilizer was done. Fertilizing was done. We are talking of compaction now, just to immediately increase its density, to impart its strength. It may be clay soil or it may be sandy soil. We said that. We said that in case of sandy soil, let So compaction to consolidation is journey. Compaction to consolidation. I won't find a person with compaction later on was available like consolidation. That's not properly stated. So we move after silence, because silence is also sometimes part of study. Soil mass consists of solid and voids. There may be air or water involved in void if some compressive load applied to soil mass. Then its volume decrease because of reduction in volume, of under pressure is known as compressibility. If soil mass in volume under pressure is known compressibility, and if it's fully saturated, if soil mass is fully saturated, reduction in volume can take effect only when water is swelled out. When a structure is built on soil, mass then structure exerts some pressure on soil mass. Load of structure acts on soil mass continuously for a long time. Due to this load, volume of voids in soil are further reduced. This occurs due to expulsion of water from voids of soil mass. Thus, gradual compression of soil mass resulting from long-term static load such as structure, building, or self-weight of soil is termed as consolidation. When a structure is built on soil mass, then structure exerts some pressure on soil mass, and due to load of structure acts on soil mass continuously for a long time. Due to this load, volume of voids in soil is much reduced due to expulsion of water from voids of soil mass. So gradual compression of soil mass resulting from long-term static load such as structure, building, or self-weight of soil is termed as consolidation. Thus, gradual compression of soil mass resulting from long-term static load such as the structure, building, or self-weight of soil is termed as consolidation. Consolidation effects due to expulsion of water from pore of soil. Compaction is different than consolidation because it is done by mechanical means, and compaction affects due to expulsion of air from void. That's simple definition of compaction. Simple definition of consolidation, sorry. Now, there are various chapters here. I want to point talk, not talk in just darkness. Testing I will not do now. Now there's one talk here, soil classification and its structure. Soil classification and its structure. We know different types of soils having different engineering properties are found in universe. Efforts have been made to classify these soils into different groups having reasonably similar behavior. Different types of jobs may need different classification systems. For example, now different types of jobs need different classification. For example, classification system suitable for a road project is not suitable for earthen dam. So main aim of soil classification is to arrange various types of soils into different characteristics, groups according to so main aim of soil classification is to arrange various types of soils into different groups according to their engineering properties. Soil processing similar characteristics can be placed in one group. Soil classification can be done for different types of engineering works, but certain general behavior of soil are common for all purposes. There are many systems of soil classification, but for general engineering purpose, soils can be classified in following types. Let us see what are those types. Grain size distribution. Grain size distribution, that's number one. Then there's US Bureau of Soils triangular classification system. Then there is soil classification according to Casey-Granidy plasticity chart. Then Public Road Administration classification system has also soil classification according to Casey-Granidy basic guarantee, passes chart, and public road signals. Then it is soil classification, then public road administration classification system, also known as PRA, and unified soil classification system, then Indian standard classification system. Okay. After that, unified soil classification system and Indian standard classification system. Now, grain size classification. Grain size as first one, that is classification of soil are being classified according to size of grain. Many agencies have proposed grain size classification. Important among them are Bureau of Soil Classifications, MIT, and ISI classifications. Let us say US Bureau of Soil Classification and Grain Size class. In grain size distribution, in this system of classification, soil are classified according to size of grains. Many agencies have proposed grain size. Important amongst are US Bureau of Soil Classifications, MIT and IS. Rolling classification system, and A is US Bureau of Soil Classification based on grain size. Grain size, the following table gives type of soils and classification slabs. Now here we have, let us say, a list which is type of soil and range in mm. What is that? Let us say gravel, GRAVL gravel, 2 mm and above. Gravel is about 2 mm. Fine gravel 2 to 1 mm. First is gravel. Gravel is about 2 mm. Fine gravel 2 mm to 1 mm. Coarse sand 1 mm to 0.5 mm. Medium sand 0.5 mm to 0.2 mm. Very fine sand 0.1 mm to 0.05 mm. Silt 0.05 to 0.05 mm. So we can say fine sand 0.25 to 0.2 mm, very fine sand 0.1 to 0.005 mm, and silt is 0.05 to 0.05 mm, and clay is below 0.005, and it should be actually 0.002 to 0.0002 mm as clay. Again, see, these are only 8 items given here, and is worth understanding in millimeter size of grains. So this is the classification purpose, nothing else means. It says, let us say gravel. Let me show you gravel. This is point. Let me show you this better. Showing is sometimes better than speaking. So I'll show you that. It says gravel, then fine gravel, then coarse sand, medium sand, fine sand, and it says very fine, and let's say like this is given here, and what is there to say? It says this table says gravel is about 2 mm. 20, 2 mm, 3 mm, 4 mm, about 2 mm. Fine gravel is 1 to 4.3. So gravel, 2 mm, about plus 2 mm you can say. Fine gravel 2 mm to 1 mm. You can say coarse sand. Coarse sand 1 to 0.5 mm. Coarse sand is 1 to 0.5 mm. Medium sand is 0.5 to 0.2 mm. Fine sand is 0.25 to 0.5 mm. Very fine sand 0.1 to 0.0. These are classifications, so let's go down like this. Gravel, fine gravel, medium gravel, fine gravel, coarse sand, medium sand, fine sand. So, very fine sand. After that, that is expressed in following forms as shown. There is clay, silt, that there are shown in light is again off. Light is again off. So it is clay, silt, very fine, medium, coarse sand, fine gravel. And this is between 0.005 mm to that is, can say, if you read like this, it is same but in different mode. Then say means same thing but in 10⁻⁹. Let's now go to MIT and IS classification. MIT and IS classification. G. Gilboy of MIT proposed MIT classification. IS classification is also similar to MIT system. This was, in this case, we would say same format of claim sector as written here. Size here will write IS items. Let's say IS classification is also similar to MIT system. So same in it was size, and that is let me speak first for item 1 tabulation form that was and clay is 0.005 mm. Clay is 0.0, clay is 0.005 mm. Down here is gravel, this is 2 mm, and silt is 0.05, 0.1 further down, 0.2. Then MIT IST, now it is MIT IS classification. It says clay is 0.002 mm and then fine is 0.006. This is let us read like this. Clay in the system MIT is 0.002 mm, then finite percent fine is 0.006, medium is 0.002, this is 0.003. It's very easy to remember MIT classification system, which is evident from figure. One has to remember only two numbers, 2 and 6. One has to remember 2 and 6, 0.2 and 6, upper limit, lower limit of something. One has to remember two numbers, 2 and 0.6 mm in is coarse sand from 0.6 to 0.2. This is gravel, and now it is lower limit of 2 mm is gravel, and from 2 mm to 0.6 mm is coarse sand. From 4 to 6, 4.2 is Now go further that US Bureau of Soils triangular classification system. Now it says that system which assumes that soil consists of fractions of sand, silt, abuses, and abuses, contains abuses. Now what's that? It's very complicated subject because no right now it's difficult to know. Now different states has given classify US Bureau consists which assumes that soil consists of fractions of sand, silt and clay. Sizes and coarse sizes about 2 do not exist. Different names have been suggested by them to different soil compositions. Different names have been suggested by them to different soils composition. If percentage of soil, percent of sand, silt and clay are known to be mixture. So let's go now to US Bureau system, and that is name, percentage, percentage silt, percentage clay. Let's say it's a table. This goes and says that if the proportion of sand, silt and clay are known in mixture, soil can be located in triangular chart by giving alone two arrows. Different names have different compositions are given. And texture, that's what you got. Now let's say sand, then sandy loam, silty loam, sandy clay loam, silty clay loam, sandy clay, silty clay, and silt. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 classes are there, starting from sand and going down to silt. Starting from sand means sand. First of all, there is sand, then sandy loam, silty loam, sandy clay loam, silty clay loam, sandy clay, silty clay, and silt. Sand percentage, sand is 80 to 100 and silt is 0 to 20, clay is 0 to 20. Oh my god, लाइट दे दो यार, थोड़ी देर बैठना है, क्या करेंगे यार, what to do? Now let's go as this what to do, light or no light. I had just few minutes more to finish that. Difficult. So sand percentage is 80 to 100, silt percentage is 0 to 20, clay percentage is 0 to 20. Sand loam 50 to 80%, silt 0 to 50%, 0 to 20%. Good. Loam 30 to 50%, 30 to silt is 30 to 50%, clay is 0 to 20%. Silty loam is 0 to 50%. That is sand. Percentage silt is 0 to 30. Percentage clay is 20 to 30. Clay loam 20 to 50% sand, 20% silt, 20 to 30% clay. Silty clay loam is 0 to 30% sand, 50 to 80% silt, 20 to 30% clay. Sandy loam, sandy clay 50 to 70, sand 0 to 20 silt, 30 to 50 clay. Silty clay is 0 to 20 sand, 50 to 70 silt, 30 to 50 clay, and silt is up to 70%, and percentage silt is sand is up to 70%, silt is 80 to 100%, clay is 0 to 20. Again I read this is very important one, and before that I show you as well. This is no problem here. This is that list of that's why I read from here so that it's worth clear to everyone. It's slow little, but it's very important. I read again. So I'm reading name of classification of material, that is name of soil. Then it is percent is sand, then percent is silt, percent is clay. Otherwise, others are different. And this is now sand. Sand, what is that? 80 to 100% sand. This means other items are silt and clay. Silt is 0 to 20 and clay is 0 to 20. Then other item is sandy loam, in which 50 to 80% is sand, 0 to 50% is silt, and 0 to 20% is clay. Loam 30 to 50% is sand, 30 to 50% is silt, and 0 to 20% is clay. Silty loam 0 to 50% is sand, 50 to 100% is silt, 0 to 20% is clay. Sandy clay loam 50 to 80% is sand, 0 to 30% is silt, and 20 to 30% is clay. Then clay loam 20 to 50% is sand, 20 to 50% is silt, and 20 to 30% is clay. Clay loam is now silty clay loam. Sand is 0 to 30%, 0 to 30% sand, and 50 to 80% is silt, and 20 to 30% is clay. Sandy clay 50 to 70% is sand, 0 to 20% is silt, and 30 to 50% is clay. Clay. 0 to 50% is sand. 0 to 50% is silt, and 30 to 100% is clay. Silty clay. Zero to 50% is sand, 0 to 50% is silt, and 30 to 100% is clay. Silty clay, 0 to 20% is sand, 50 to 70% is silt, 30 to 50% is clay. Silt, 0 to 70% is sand, 80 to 100% is silt, 0 to 20% is clay. This is for different names have been suggested by them to different soil compositions. The percentage of sand, silt and clay are known in a mixture. Soil can be located in triangular chart by going along arrows. Different names having different compositions are given to 42. So based on this result, there is a triangular chart here. There is textural classification chart, we call it. On right, on base of this triangle, there is silt mentioned 0.05 to 0.05 to 0.005 mm. On left side of triangle, there is sand, that is 2 mm to 0.05 mm, and on right side of triangle, there is clay, just less than 0 to 0.05 mm. There is a division on textural classification chart. There is a division on base, this triangle, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And that 100 is again starts 0 on right side, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. And then a 0 starts on left side, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this continuation of 0 to 100, then 0 to 100, then 0 to 100 means 0 and 100 are at all three apexes. This means 10 and 90 are in same line on triangle, 10 and 20, 80, 37, 30, 30, 70, 40, 60, 50, 50, 60, 40, 70, 30, 80, 20, 90, 10. And also if you say other way, means in this way and in that way, also you can say, if I say 0, 100 or 1, then next one in parallel is 10, 90, 20, 80, 30, 10, 30, 90, 30, 70, 40, 60, 50, 50, 60, 40, 70, 30, 80, 20, 90, 10. And this is also same 10, 9, 20, 80, 30, 70, 40, 60, 50, 50, 60, 40, 10, 30, 70, 30, 80, 30, 90, 0 and 100, 0. So you can say sum on all lines. Sum of all lines is on opposite to each other, 100. That's important point is there. Now this is just a graphic representation, and there are various areas which let's say in bottom you can say there are so how many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions this way. So there are 10 divisions from base to apex. Then there are 10 divisions from, you can say, right side to left side, and there are 10 divisions from left side to right side, all parallel in both sides, and this is also from base. So this is, I'll show you this triangle, very important one. And so it is giving in triangle fashion. You see this base here, and then you can say on one side base is sand, other one is clay, and other one, see. This is design of this graphic representation of components of soil. Base is for silt, left side is for sand, right side is for clay, and base silt says 0.05 to 0.005 mm, division of 10, and again sand to 0.05 mm, clay is again less than 0.05 mm. Now it is textural classification chart. Name is textural classification. Now in opposites in sides 40-60 and 50-50. In this portion 40-60, if you see from top apex, from apex to down, 40-60 line and 50-50 line, this is covering by clay. This clay covers this. Then if you go down to 60-40 line, in middle there is A written. And if you go down to further 60-40 and 10-30, this coverage is sandy clay on 60 end corner and silty clay on other corners. Sandy clay on sand end and silty clay on silt end. And if you go further down to 70-30 and 80-20, you'll find end one is sandy clay loam and clay loam in between, and silty clay loam are one. Then 80-20 and 90-10, if you check, sandy, loam and silty. Then go down to 90 and 100, find sand in first triangle, second triangle, sand, loam, silty. This is a division given by either division of this chart, and this US Bureau of Soil, US Bureau of, I'll show you again so that should be a little clear, no confusion was there. It's very important for understanding the point. It's almost to say, I'll show it again. You can see this I'm talking of. If you see this sand, loam, lie like this every year. If you see 50, if you see down another one, clay is given them 60-40, 50-50, and then is on sides and 60-40 and others. Like that, all textures of clay compositions are given there. That and A is written at that point, and say now, only and so actually. Go and say next description of this. That's I need to say it's different types of cells have been represented in triangular form in this figure. One side of triangle represents sand percentage, another side silt percentage, and third side clay percentage. There is a big shortcoming in this system, that there is no mention of plasticity characteristics of a soil. Hence, even if a soil is in category of clay, according to grain size, it may not possess properties of plasticity. A good example of this is fine rock floor. Its particle size may be between 0.001 to 0.002 mm, but does not possess plasticity. According to this classification system, it shall be termed as clay, which is not true, because clay must possess plasticity. While using short lines are drawn parallel to three sides of equivalent triangles are shown by arrow in key of this. For given percentage of three constituents, sand, silt and clay, forming soil, say for example, if a soil consists of 30% sand, 30% silt and 40% clay, and if their lines are drawn, then they intersect at point A, situated in sector termed as clay, and such soil shall be named as clay. Now, well, just for reference, it's given. We'll go to Cassegrain plasticity chart. It's a plastic chart. Cassegrain. Soil classification according to a Cassegrain. I'm sorry I could not, due to electricity failure, I was lazy. I wasted some time because it's very hot. Soil classification according to a Cassegrain plasticity chart. In this, there is a figure. You can say there are 6 divisions in this. Base of this graph is this chart is 0 to 100, and that is there is liquid limit on top. If you see, there is a rectangle on top is liquid. This direction liquid limit, and up direction on left is given 0 to 70. It's also plastic index, and in this 6 divisions, there is one which is inorganic. I'll show you this. There's one which is inorganic cells of high compressibility and organic clay, and this is where liquid limit is increasing. It is inorganic cells of high compressibility and organic clays. It covered within 50 and 60 liquid limit area, and on this side there is an A-line division that actually controls this area. A-line, which starts at down point at 20 and goes to between 50 and 60 on other side, on plastic index side 50 to 60, and liquid limit size of 20. And it says if you start from 1, on which right side this is inorganic silt of high compressibility and organic clays. Then if you go to next one, that's between the number 2, which is inorganic silt of medium compressibility and organic cells, and number 3 indicates inorganic silt of low compressibility, and number 4, which is above A line. These are all 3 below A line. Now above A line is and I can say inorganic clays of low plasticity. Number 4 and 5 is inorganic clay of medium plasticity, and number 6 is inorganic clays of high plasticity. And let's say Cassegrain has made a use attribute limits for clarifying soil, which is based on value of plasticity This figure shows liquid limit has been shown on x-axis and plasticity index. Cascade line A has been drawn, which slope is having equation, that is plasticity index is equal to 0.73 bracket liquid limit minus 20 ordinates corresponding to liquid limit of 30% and 50%. Divide whole chart into six regions. There are below line A and 3 are above. Names of all 6 regions are here below. Let me show you this chart first. A category chart for plasticity index classification depend at above limits. Does it say? You can see this liquid limit on x-axis and plasticity index on left one, or horizontal axis liquid limit. That's A line here at 0.20 and near more than 50 on number 1, and below 3 areas and above line 3 areas, and the plasticity coefficients, what are these areas indicating. This is that one. This is A category classification at above limit. That will be the first. What says? Inorganic cells of high compressibility and organic clays, as we said, number 1. Number 2 area, inorganic cells of medium compressibility and the organic cells, this is number 2. And number 3, inorganic cells of low compressibility, all 1, 2 and 3 below line of A. Above A, inorganic clays of low plasticity, number 4, and inorganic clays of low plasticity, number 4. Number 5 is inorganic clays of medium plasticity, and 6 is inorganic high plasticity. So you can say first one is second one, third one, fourth one, and sixth, all that. If liquid limit and plasticity index of a soil are available, its region can be located on plasticity chart. From chart you find that organic clays fall in same region as inorganic cells of high compressibility. From this chart we find that what we find? We find that organic clays fall in same region as inorganic cells of high compressibility. And organic cells fall in same region as in inorganic cells of medium compressibility. Distinction between organic and inorganic soils can be done on basis of order, which is emitted by organic soils. Sometimes for making a distinction, liquid limit of natural air, dried sample and over-dried sample is found. If soil contains organic material, liquid limit value of over-dried material sample will be less by more than 30% as opposed to liquid limit obtained from natural sample. So this is only their difference of smelling from one. Now I'll repeat this sketch for you, it's better, because then after is public road administration soil classification system, and which shall be followed by unified soil classification, and further followed by the Indian standard soil We'll take up in next one because this is a little bigger. You'll find that when I'm understanding from both, and then we have taken soil structure already. So these are classifications of soil which are more important. So we'll take up this. So we have taken today in this classifications, you can say we have taken grain size classification, and we have considered US Bureau, BMIT and IS classifications, US Bureau of Soil triangular classification, and the soil classification according to A category plasticity. A category, I'll show you again this one because it is speaking something, and that speech must be made clear before we do something else, If you can show this, yeah, that's right. Is that you might have seen in some courts, you see 1, 2, 3, 4, 5, 6, a line A, and 3 areas above and 3 areas below, horizontal liquid limit, vertical plasticity. On left side, less plasticity. On right, towards right, when liquid limit increases, it's high plasticity. On left side, it decreases, it's low plasticity. Soil indicates 1, 2, 3, 4, 5, 6 areas, just for indicating where your soil lies in. Organic and inorganic connections have been described separately, and you can identify them based on your smelling only, because organic soils smell. It says that liquid limit and plasticity index of the soil are available. Its region can be located. It's simple, understand that. Based on plasticity index and liquid limit. And from this chart, organic clays fall. Organic clays, that is, you can say, organic clays falls in same region as organic silt. This is organic clays. It falls organic clays here is number 1. It says inorganic silts of high compressibility and organic clays. So it says organic clays and inorganic silt, they are falling in same region. That's what it's saying. As in organic silts of high compressibility, and organic silts fall in same region as organic silts of medium compressibility. So this is inorganic clays of medium plasticity, and this is inorganic silts of low compressibility. That's number 3. So it says that from chart we find that organic clays fall in same region as inorganic silts of high compressibility, and organic silts fall in same region as inorganic silts of medium compressibility. Distinction between organic and inorganic soil can be done on basis of order. The order which is emitted by organic cells. So sometimes for making a distinction, liquid limit of natural air dried sample and over dried sample is found if soil contains the organic material. Liquid limit value of over dried sample only less by more than 30% as compared to liquid limit obtained from natural sample. So now again I say number 1 is they have inorganic silt of high compressibility and organic silt. This is in the lower lower area 1, which is in range of liquid limit between 50 and 100, and if you see liquid limit, that is on 50 and 50 number liquid limit, it is plasticity index about 2, around 2, and 100 is the plasticity index is about 55. That is reason this covers this range of liquid limit 50 to 100 and plasticity index, that is between 50 to this is up to 2. On left of 50 at 0.50 WL it's 2, and at 0.100 it's 55. And if you, this is number 1, and number 2 area is inorganic cells of medium compressibility and organic cells, and on this liquid limit is 30, its plasticity index is say 5 or 6, and in 50 liquid limit 50 it's around 2, and this coverage is here for inorganic silt of medium compressibility and organic cells. Then you go to number 3, that is on this at point WL20 plasticity index is 0, and at point WL at point liquid limit is 20, it is 0 plasticity index, and where liquid limit is 30, this is plastic index is 5 say. Now go to, and this says area number 3, inorganic silt of low compressibility. And we go on down to number 4 up this line number 4, where this area coverage here is 0 liquid limit, and it's continuous up, liquid limit is 0, there's no line, and is above line, this number 4 is inorganic clays of low plasticity, because, and then you can say in this up to 20 it shows area 4, 20 liquid limit, then it's inorganic clays of low plasticity, and when you say number 5 about in that area increasing clays of medium plasticity and inorganic clays of high plasticity. So there are 6 such divisions here, and you can say number 1 is inorganic silt of high compressibility and organic clays. Number 2 is inorganic silts of medium compressibility and organic silts, and number 3 says inorganic silts of low compressibility, and 4 says inorganic clays of low plasticity, and 5 says inorganic clays of medium plasticity, and then it says number 6 says inorganic clays of high plasticity. That's what this classification is about. You can say this is A grade. Public road will tomorrow will take there. So what we understood first of all classification, then we start talk little about consolidation. Consolidation we are not defined, we are not going in depth, but consolidation we define that in context time continues with the weight of soil or with some imposed load. Yes, water particles are taken out automatically, scroll out. Compactions relate to air voids, while water particles, and of course further densification of soil continues for decades, and that stage where completely is gone out, water particle, and final solidification of total solidification soil achieves. That's called consolidation of soil, which is very important part, and we also are going to understand what is this classification of soils based on, you can say, size of grain, and based on, for these same qualifications are based on US Bureau soil triangular matrix, and then also we go to A category, public road administration, and then we have to go through this unified soil classification, and of course Indian standard soil classification we have to go through, and then you can say compaction test, field control, this compaction test model proctor needle we had a little understanding, and laboratory compaction test we are not talking now, just talking basics behind that. How to do compaction field, machines we have gone through, and what are factors that affect your your says that factors affecting compaction, that is, you have gone through your moisture, water or moisture contents and soil types, and say how compaction affects the structure, how compaction affects permeability, how compaction affects compressibility, and how compression affects compression affects swellability and shrinkage, and how compaction affects pore pressure, and also compaction of shear strength and shear strength chart characteristics is gone through here. Then you say number of passes, how to find number of passes for rollers and field trial for moving passes, so that no additional pass will allowed be done to save time and money. And I'm not going through machines as equipments we have to use for that purpose. This is all compaction, etc. And we'll go through. We're not going through any technical theories till now, and that we will take later on, because first I want to just define what's here. That definition must be understood properly, otherwise there is no meaning at all. And then engineering properties are having a requirement also here for, or this is I say that is the beginning chapter there is, and that is engineering properties soils gives introduction and phase diagram and all that gives. But important point is definitions also given here, means what is like what is phase diagram, that what's porosity. Porosity, for example, if is mass, parameter percentage positivity of soil, porosity of soil means ratio of volume of oils to total volume of soil mass. Then void ratio, and then degree of saturation, water content, mass unit weight, then unit weight of solids, unit weight of water. Sorry. And then the relative density, it is a minor definition, but important one. This we have to understand clearly before. And then sieve analysis, etc. Particle size distribution is very important. Simple soil test will take into consideration that should be determination of water content, determination of specific gravity, possibly sieve analysis, which may be consideration of the IS sieve, BS sieve, ASTM sieve, and calculation of results, and strokes for wet small. So there will be something not something here, which is considered practically important. We'll do that. Then I shall avoid many tests because tests will take time, but we'll know. In fact, so we'll take element designs later on. Now, because I have to share with you soil reports, and that's only purpose of this information sharing with you prior to jumping on that, because it requires that very important one. And also in the soil investigation will take care of many items: soil investigation, subsoil explorations, and it's written that an engineer must possess reasonable accurate information about soil conditions, its arrangements and physical properties before he is in a position to design a foundation. It's clearly written here, an engineer must possess a reasonably accurate information about soil conditions, its arrangements and physical properties before it's in position to design foundation. Field and laboratory investigations required to get this essential information are known as soil exploration. Due to very complex analysis nature of deposits, no one method of exploration is best suited for all conditions. Thus, object of soil exploration may be outlined as follows. And those are depth, extent, nature and variation of soil strata, physical properties of soils encountered, depth to underlying rock bed when necessary, and approximate value of strength and compressibility of soil bed, seasonal variation in groundwater table, selection of foundation types. Now, first step is to inspect site and study topographical features for deciding future program of exploration. Many informations can be gathered from local people regarding type of soil, seasonal variations of groundwater table, ice level, and types of cracks and failures in existing buildings of that area. But for important, a program for soil investigation, it's evident that a careful stratigraphic study surveys to is first substantial requirement for useful soil investigation, and improper program for a given project depends on type of project, importance of project, nature of subsoil, and it's, you can say, in general, large dam projects would usually require more thought subsoil investigation than would be highway project, even if cost of two may be comparable. Soft clays also require more investigation than to gravels, and two obligatory steps in whatever subsoil exploration may be outlined as follows: an investigation of general geological character of site to make exploratory notes, exploratory drills holes that provide more specific information regarding general characters and thickness of individual strata. Important data on subsurface. Put a fan study. Important data on subsurface conditions can be obtained from maps and publications of central, state or institutional geological surveys from central and state agencies connected with highways, buildings and large projects like, detailed data on foundation conditions is highly developed. Areas may be found in technical political sleeve. A study of stereoscopic aerial photographs facilitate detection of slide areas, burial channels, faults, and other subsurface irregularities. Most natural soil deposits can be classified as one of following principal types: river channel deposits, floodplain deposits, shore deposits, glacial deposits, windley deposits on this. In case of profile is erratic, efforts should be made not on soil SEM, not on obtaining accurate data regarding physical properties of individual soil samples, but on collecting reliable information about a structural pattern of subsoil. With increasing complexity of soil strata, results from elaborate laboratory investigation decreases rapidly and often become useless or misleading. Such erratic soil profile are by far most common. This is some note of soil investigation that are written here, and then we have to decide, we'll read this, and number of pits and borings what we have to do, and depth of exploration, where borings to be required 11 for that, and then we have to see, and groundwater level, And then classification, how to do that, various methods of exploration are there. It may be open test pit, maybe boring, tube boring, auger boring, wash boring, precision boring, diamond drilling, rotating, geophysical methods and subsoils or surroundings, open test pit and tube boring, like that. So many methods are there. You'll see advantages and disadvantages, wash boring, etc. What we have to do. Then we can say, and bore tests are there. We have to understand them. How can we use them? And then we can say that diamond, all drilling methods are there. So, seismic refraction, geological methods are there. Then there's electrical resistivity method is also there, and that's in this method two models of, we'll see that one. And then we can say subsurface soundings, standard penetration test is also there, which gives penetration resistance and blows, and it says that standard penetration test is very important for everybody. I just read the information, preliminary information. Standard Indian standard provides guidelines for this test. It is performed in clean hole 55 to 150 mm in diameter. A casing is drilled, mud may be used to support sides of holes. A split spoon sample of 50.8 mm outer diameter and 35 mm inner diameter is driven into undisturbed soil bed at bottom of hole under blows of a 65 kg hammer with a fine free fall of 75 cm. Minimum open length of sampler should not be less than 60 cm. Sampler is first during. So this will take on later on, then we will take value of n from the value of n, which is very important one. It is defined, of course, in tables. Actually show some of empirical relations of soil coverage and penetration resistance. And then example says if n is 30, it is dense, dense medium, like that. And for cohesive soils, we will take penetration resistance n and unconfined compression. For instance, is this. And then you can see like that. You will sample. Also, we move this in this direction slowly because it's also not easy. I would like to say that soil engineering is very much important for every one of us. We should not ignore this subject, because every building, every structure, whatever you do, ultimately it is soil that is responsible for survival and stability of the structure. And if it's not done, if you do not care for that, you miss soil in every structure. All your efforts you do on designs of that are futile, I can simply say. If efforts are futile, you think you want futile efforts, it's up to you, but I don't accept that. You must know what is soil, every one of you, whatever your qualification by education is, you must know what is soil. At least we are discussing, you must know. Report you may get from laboratory, not difficult, but this should be professional reporting, not just one professor goes from university and surveys. No, that's not correct way. Correct way is professional laboratory, fully equipped, having technicians and qualified report writers, and civil engineer is supposed to interpret that. Whatever recommendation comes, civil engineer has to test on that. I have seen many reports and I found errors in those reports. And those errors were brought to notice of structural engineer, of consultants, and you change the signs because it happens. You cannot blindly follow what is given in report. That is only recommended, and those people don't have structural knowledge. Those who write report, they are not civil engineers. Unfortunately, it is job of civil engineer, but I don't know why they run from such responsibilities. It's a baseless argument that it's not part of civil engineering. If it's not part of civil engineering, it's part of nothing then. This is a real material, number one material for construction is soil. All other materials are secondary. If soil, just like saying, if structure fails, architecture fails. If soil fails, engineer fails. Simple. If structure fails, we say architect fails because his work doesn't work. Structural engineers, structure is more important than architecture as far as stability, as far as existence is concerned. Same way, if you have good designed, very well designed, but your foundation is defective, it's exclusively based on recommendation by someone, no, do not do on recommendation. You have to change your working habits. You can't pass responsibility on to someone. It's duty of civil engineer and structural engineer because they are designing. You cannot say, I am putting disclaimer here. You cannot put disclaimer on that. You have to share responsibility. Soil fails means everything fails. That's point to you. With this, I would say to continue this and hope you may like it. Like it, don't like it, it's up to you. I am only suggesting, I am only sharing my task to you. With this, I thank you very much, gentlemen. See you for next portion of soil before I start talking to you about soil reports, 2 or 3 files I have. Thanks you very much. Dhanyavad. Masalam. Thanks once again.